Hello, my name is Sigurdur Hafstein. I'm in Iceland, and we have evening, so I have three little girls here. I hope they don't disturb too much. They're promised to stay in a room and be quiet, but you never know. So yeah, welcome to this talk about Lyapunov functions by integrating ODEs. And so the outline of this talk is, first I want to tell you a little bit what I want to talk about. So what is this really about? And this talk is about a project for a numerical analysis course for undergraduates. So I will tell you a little bit about the course too. Then I will talk a little bit about exercises and projects in general. And then I will describe the project and finally make some conclusions. So, well, I'm teaching numerical analysis, which I very much like, but designing good projects involving programming then in numerical analysis for a large group of students with different backgrounds is, well, it's not easy. Because, well, first of all, the assignment has to be manageable for all the students, basically, that are supposed to pass. But it would also be very nice to have some depth so in the project, so that let's say some students or the more interested students actually get interested in the subject and start to ask questions. Yeah, I think about the subject more deeply. So I will describe this project that was assigned to the students of this numerical analysis course, University of Iceland. And the assignment is essentially to numerically compute the length of solution trajectories of ODEs with a stable equilibrium point, but for many different initial conditions. It's not difficult to do this, but the results are somewhat surprising. And so some students actually got interested in what was happening there. And yeah, I will describe the project, its solution using MATLAB just a little bit, and then the underlying mathematics in some more details. And then I will discuss the pedagogical aspects and the results, well, in terms of success and shortcomings. So first about the course. It's a second-year course in a 3 years undergraduate program, bachelor's program. It's 6 ECTS units, which are the standard European units for from Bologna. Basically, it's like a normal course. This means that if you have 2 semesters, they should take 5 such courses per semester. And there are 2 times 80 minutes lectures per week and 1 times 80 minutes exercise class per week. And this goes on for 14 weeks. So the semester is 14 weeks. This course has 120 to 150 students, 2/3 are male, 1/3 female, and they are either studying mathematics or applied mathematics, and these actually get additional theoretical course where we prove, well, all the results, more or less, of the course, the methods. Then we also have students of physics, but the mass of the students are actually engineering students, so mechanical, industrial, chemical, civil, environmental, and electrical engineering. But it's also an elective course for geophysics, computer science, and software engineering, and chemistry. But most of the students are really from engineering. The prerequisites for the course are computer science, so they should be able to program in, well, MATLAB or Python. It's linear algebra and analysis 1 and 2. It's basically calculus of 1 variable and then multivariable calculus. And it's also recommended that they have passed analysis 3, which is then about ODEs, Fourier series, transforms, and complex analysis. So I just wanted to go quickly through the course description and the skills they are supposed to have after having passed the course. So I think it is a very classical course on numerical analysis. So it's like fundamental concepts on approximation and error estimates, solutions of systems of linear and nonlinear equations, LU decomposition to solve linear equations, or PLU with the partial pivoting, QR decomposition and singular value decomposition, then interpolating polynomials, spline interpolation, regression, numerical differentiation, integration, extrapolation, numerical solutions of initial value problems, or ODEs, also multi-step methods, and then at the end we do some numerical solutions to boundary value problems for ODEs. So if they go any further in this direction, then we do PDEs, but we don't start them here. We just prepare everything. And yeah, and then we define learning outcomes. So, well, they should have some knowledge and understanding. So they're supposed to actually more or less know the stuff we did. But the skills are, so to complete this course, the students should be able to formulate a simple mathematical problem as a numerical problem, implement it on a computer and compute an approximate solution. Estimate the error of the numerical solution, use some computer software like Anaconda, Python, or MATLAB for programming, computing, and performing some numerical experiments. And also to validate the results of the numerical computations. That's very important. And then also to use the concepts and the results of the course to develop an advanced algorithms for simple problems the student has not seen before. So actually to have understood really what we did. And just to give you a simple example, like the theory, which is then covered in the lectures, and I take it as an example, Newton's method to compute roots of functions. So f is a function from R to R. We also do it later than for in the multidimensional case. So in the lectures, we explain the formula, explain like where it fits in the theory. So it's a special case of fixed point iteration, how fast it is, so quadratic conversions to simple roots, then also explain that if the roots, if a root is not simple, then we only have linear convergence. Also that we don't have any guarantee of convergence, so basically we have to start close enough to the root to a root to actually find it, and then we show how we use it. Do some examples on the blackboard, and also maybe show them with a computer a little bit. And weekly they get some exercises they're supposed to like solve and turn in, which are then graded. And that would then typically be like apply Newton methods to approximate the root of some function like sine of x close to 3. They should then do it by hand, maybe 2 or 3 or 4 iterations, but also then to write a short program to actually do this. And then, well, that we have also then covered in the theory. I mean, when do we stop searching? So when we must have some criteria to tell us that we are close enough to a root like that. Well, that the solution is not changing, numerical solution is not changing or not changing within some tolerance. It's not changing much. And now we have also always have the question, well, what skills does a student get from studying theory and doing these routine exercises? So will the student get the skill to actually solve real world problems, or, well, will the student get the skill to solve routine exercises? And probably more of the second, but hopefully they can build up that later to do something more. But because of this, and because we wanted to be able to solve like more real problems, we also have 2 larger group projects in the course, and they count 30% in the final grade. And the textbook we're using is Numeric Analysis from Timothy Sauer. It's a very nice book, in my opinion. And in the book, there are several reality checks, which are basically projects like this. And as example, is the kinematics of the Stewart platform, which is used in flight simulators and has other applications, or positioning using GPS. So there we would use some approximation, and we have some satellites, and we have a signal, and they explain the theory, and they do some computations. That's actually very nice, these reality checks. Also motion control and computer-aided modeling, and there's even a simple audio codec. And Well, this is very nice, I think, because this is very inspiring for at least some of the students that to see that these methods actually have real applications, and hopefully gives them some sense in the Newton method, but you actually use it then to solve some real problem. And what I also think is very important is that it's not, these methods are something, well, you want to solve a real problem, you combine methods. So you use this one to find a root, you use something else to make numerical integration, whatever. What I wanted to do, and that is basically what this talk is about, is that, well, I come from mathematics, so I wanted to have a nice, let's say, reality check, but something that is not connected to engineering or technology, but something that is connected to mathematics or even physics. And yeah, my field of study is dynamical systems, and in particular stability and Lyapunov functions. And well, the constraints of the project is, well, it cannot be too long because it only counts 15% of the final grade. So, and it cannot be too difficult because, well, the average student, or actually, I mean, all students that really try to solve the problem should be able to do it. And the project I did was the numerical study of the van der Pol oscillator. The van der Pol oscillator has an unstable equilibrium at the origin and then a stable limit cycle encircling the origin. It's like one of these classical examples in nonlinear dynamics. And I just go through it, and this is typical, very similar to how the reality checks in the book by Sauer are, is that it starts slowly and always gets a little bit more and more. So here we have, well, and actually I used the time-reversed van der Pol oscillator because I want to have a stable equilibrium at the origin. So basically I just reverse the time with a minus in front of the right-hand side. And the first objective then of the project is simply to use ODE 4.5, so the standard solver in MATLAB, to generate some solution trajectories and see what is happening. And well, because this is the time-reversed van der Pol oscillator, we have a stable equilibrium at the origin. So if we start somewhere, we will end up there. And if we start inside of the this area here, and if we go backwards in time, we should end up at the periodic orbit. Then they were supposed to implement, well, the standard Runge-Kutta method about before. Well, use some larger time steps, and basically it's the same solution, just not so nice because the time steps are much larger. But then, and this was like the final part, and the part I thought was really interesting, that is on a uniform grid, rather large grid, so 101 times 101, on basically an area that covers this periodic orbit. They should compute the length of the solution trajectories to the time-reversed van der Pol oscillator over some time interval. And just after experimenting a little bit, I choose the time interval of length 4. And they should use the Runge-Kutta method. And then they were supposed to use numerical quadrature. And they were supposed to use 100 time steps. So it's, well, even on a rather slow computer, it doesn't take too much time. And, well, the nice thing about the theory, in my opinion, is that, well, if we have here a solution to this differential equation with initial value psi, and we compute the length here, L of psi, so this is the length when we start at psi, it will be this integral here of the norm, Euclidean norm, of the time derivative of x. But since this is a solution to the differential equations, this is just f of the solution. So basically they compute the solution here, solution trajectories, compute an f of it, oops, and the norm of f, and use numerical quadrature to get the length. And if we do this, this is what we get. And well, actually there is a cutoff here. We don't go higher than 16. So if we get a length that is larger than 16, we just do 16. And this is what I was hoping that the students find interesting. Why does it look like this? And well, if you're into dynamical systems, you will know that this is actually a Lyapunov function for the system. So it's like some kind of a generalized energy, and the stable equilibrium point will be at the lowest value. So it's at the bottom. Here is just a very short explanation, of course. If you want to read about it, this is actually, I did this some years ago and I wrote a paper about it, where I then presented it at the conference, the ICCS, and sorry. And so if you want to read more detail about the project and about the solution, I also put in the MATLAB code and stuff like that, you can read the paper. But I was doing this because I was hoping that some students would get interested in why it looks like this. And well, some did. And the reason why it looks like this is then, well, the solutions, they slow down close to the equilibrium because it's exponentially stable, so it slows down, but a lot. So the solution trajectories, if you start close to it, will be actually very short. And you can also imagine if you're on a solution trajectory and you start later, it will simply be shorter. This function is really decreasing along solution trajectories. That also means then that the level set of these functions are forward invariant. So here, if you start at some level set, you can never go out of this level set again because it's decreasing along the solution trajectories. And then I could tell them a little bit about, I mean, this was not really a part of the project, but if they were interested, I can tell them a little bit about Lyapunov functions. I could even tell them a little bit about complete Lyapunov function that more or less characterize the behavior of dynamical systems, and that every ODE basically has an energy landscape or some kind of a generalized energy that describes what is going to happen. And then I could even go on and talk about the gradient-like part of the flow, and then about the chain recurrent set where the behavior is repetitive or almost repetitive, like on the periodic one. And well, I don't know what for the conclusions. I mean, I liked it because at least some of the students, they got interested, and I was hoping like that the math students, the physics students got something different than technology. Well, the reality checks in the book might inspire some students to become interested in the technology behind the project. And actually, I think many of them are. And I also find it very interesting. I also like technology, but it's less about the mathematics. And well, some of them at least saw this and found this interesting and started to ask questions. So thank you very much for listening, and ask questions if there are some. Thank you. No questions. Okay. Like I said, thank you once again for listening, and yeah, thank you. Oh, in the chat there or something. Okay. Yeah, thank you very much. Thank you very much. Bye-bye.